Okay, so OpenMP. Let's try to go into OpenMP. So at first we need to learn about how the OpenMP, the software, is organized. Then we go step by step. First, SIMD vectorization. How does OpenMP can help us? But the major point is multithreading. How to do the multithreading with OpenMP. And as you have already seen in the program, tomorrow in the afternoon we will learn. We will use OpenMP as well to apply to use the GPU. So OpenMP is a very rich software. You can do a lot of things with it. But today we concentrate on the CPU. Let's do SIMD vectorization and multithreading. So okay, let's start with the software setup. We assume now that we are on a shared memory system. So we assume we have one node of Otus, one single node with 192 cores. OpenMP is an industry standard for Fortran and C++, and usually it is supported by the compiler. It is supported by the compiler. If you want to learn about the latest version of OpenMP, please visit the website openmp.org, and on the GitHub, on a GitHub repository, there are lots of important examples. I have preloaded the OpenMP specification, which with hundreds of pages. That's the OpenMP specification, and if you have, and of course you can download it from openmp.org as well. But I have the local copy of it is located on Otus Scratch, and this is the path to that. It's anytime. It's a good way to know where to look, how the exact syntax needs to be done. Okay, great. And so this is the software, and how is OpenMP organized? We were starting from the cores, and the hardware were the cores on our node. But on the hardware, we deal with the Linux system, and the Linux system supports processes and threads. And for an OpenMP program, what we do is we have started one process and a number of threads. So the parallelization comes not from the number of processes. The parallelization comes from the number of Linux threads. So, and on top of that, OpenMP starts. OpenMP deals with the threads of the Linux system. It is a library. OpenMP has support as part of a library, but OpenMP needs to be supported by the compiler. And we have three interactions from the user side. It's pragmas, its functions, and its environment variables. So, and we on the user side, our application, our user code is exactly interacting with the pragmas, with the functions, and the environment variables. And we see these three folds we will see in our examples, which now follows. So pragmas, runtime functions, and environment variables. And the pragmas are the way to write in our code. This is essentially that's the way to go and to extend our code. And and runtime functions. These are functions which are offered by OpenMP, which you can use in our code as well. The environment variables do not appear in our code itself, but we need the environment variables to control the program evaluation at runtime. Okay. So what's SIMD vectorization? We have learned already that single instruction, multiple data vectorization. This is vector operations, and we have learned about it. And the contrast, of course, was scalar registers and scalar operations. So we need to think about vectors now from now on. Okay. And these this is supported. Vector operations are supported by the hardware, by the CPU, and there are some historical names for that. And of course, this is kind of marketing names. And very early, 30 years ago or 20 years ago, matrix smart extensions appeared on the CPUs. But then the Intel and AMD introduced SSE, streaming SIMD extensions. So these were vectors of the length 2. So of course, very short vectors. If you think of double precision numbers. So, but of course, if you think of a single precision numbers, it's 4. It's the length of 4. And if you even think of a half precision, you can have longer. You can have longer vectors. But in terms of double precision, it's just the size is 2. Very short vector. That's why later they introduced AVX2 and AVX 512, and these are AVX 512 because the vector length is 512 bits or 64 bytes. And that's why we have some kind of vector length, and 8 is not too bad. But of course, compared to a GPU, this vector length is very short. So, and on the hardware we are sitting, what do we have there? What can we find there? We need to ask the hardware. Okay, great. Let's ask the hardware, and we have some command. For that, we have on a Linux system, we have the proc file system, and the proc file system is a kind of artificial file system. It's for interacting. Linux offers this possibility to learn from the properties of the Linux system. And if you ask the CPU info, and this is as I said, supported by Linux, as if you ask the content of CPU info, you see there's MMX, SSE, and some AVX names. And this tells you, okay, the hardware, the cores you see, they have these properties. And in a second, I will show you that Otus, of course, is available to support MMX, SSE, and AVX. Great. And how can we use that? Okay, how can we use vectors on the CPU and on the system? And on paper, we know what a vector is. It's just a number of scalar numbers. And for the example, we want to evaluate a times x plus y. And for that, we introduce we do some malloc in C. So we ask for memory which is continuous or contiguous in memory. So, and this is, if you ask with malloc, then what you receive is from the operation system, you get some vectors which are contiguous in memory. So this is what we mean. They're the vectors. We talk about. We do not talk about from the mathematical point of view, but from the informatics point of view. The vectors are called vectors on our system if they are contiguous in memory. So this is a very important property. Make sure your data is contiguous. And once you do that, then you are able to write a loop on our vectors, which are contiguous. And then the loop is operating on these contiguous memory lines. And then the system is able to use the hardware for vector operations. And this loop is able to be parallelized in terms of SIMD vector parallelization. And of course, if you use standard functions from BLAS, then the code developer know that and they deal with it. So the first step, of course, is to use a function from the library, but we want to learn today, and that's why we avoid the library call. We write it by ourselves. Okay, use memory which is contiguous, contiguous in memory space. So, and for vectors, this is kind of easy. For matrices, it becomes a little bit more difficult. And for matrices, because Linux system does not know vectors. Linux systems does only know linear vectors in memory. So we need to map our two-dimensional matrices B to the one-dimensional world in the memory. And for that, we ask for memory B, and we ask for a malloc which has a size n times n. So of course it's enough space available, but on the computer this memory space is contiguous as a vector. So how does the ordering works for us? And there is some different let's say conventions. And the C convention is that the memories you think of, the matrices you think of, are follow contiguous line by line. So in the C ordering, if you go y, also if y goes one step after the other, then you follow the lines. Also this is a matrix entry B I Y, B I J, and then you go line by line. But in Fortran, the convention is the other way around. You go row, you get column by column. So, but today we don't have to think about Fortran. But please remember, if you do Fortran, everything is transposed. Okay, good. So contiguous in memory for a matrix means you go line by line to this through this matrix. Okay, and how does it look like? How does it look for matrix vector multiplication? So Bx is, if you write it down, you see that you have two loops. One loop is for the column, that's the first, and the second loop is for the line. And the j goes through the line, and you see that, of course, x is contiguous in memory, but the matrix is contiguous in memory for the line as well. That's why this is contiguous, vectorization will work. So the inner loop is contiguous, and that's why we can expect that vectorization will work. But if you have your matrix stored in a different way, if your matrix is due to some reason transposed stored, then your access here in the B, you see, if you look exactly, I have changed the argument of B here from the left to the right. And this, if you go through this loop J, this is not contiguous in memory, because J times N, of course, is not are not entries behind each other. And that's why this inner loop is not contiguous for B, and that's why no vectorization is available. So this is an ordering. If your setup of your program is in a way that you write this down, this inner loop will never vectorize. And if you force this to vectorize, the result will be wrong. Okay, good. And the other way around, of course, if we have some other mathematics. Now, if you multiply the vector from the left to the matrix, then in the C order we have a problem. Because if you now look here onto the inner loop, the inner loop is now I, and of course B is not contiguous in memory anymore. And in this case, for this operation, our no vectorization is available for the inner loop. But now Fortran is on the good side. For this operation, Fortran has the advantage. It can be contiguous. Okay, we will see it in a minute for an example. How does SIMD and vectorization work? So of course you can do that as an expert. You can use vector intrinsic functions, and they are specific for each of the compilers. So that's very nasty, let's say. That's why our way to go is we use the compilers and ask the compiler for auto vectorization. And usually the compilers do a very good job. They can do the job if we give them the memory contiguous, if we give them the vectors and the data contiguous in memory. So our task is to make our memory set up in a way that the compiler can do its job. Okay. So, and how does vector auto vectorization work? For GNU, you switch on the optimization level, and optimization level 3 is enough. And usually then your job is done. And you can ask, of course, okay, please give me a report about your vectorization. And then you add this report, this info optimized. You ask for the report, and then the answer of the compiler is yes. In my code SIMD, in line 35, my loop is vectorized. Great, successful. Of course, you can, if you have, you can switch off the optimization, but you can apply the optimization 03, and you can forbid the compiler to vectorize code, and then there will be the report will be empty because no loop will be vectorized. Okay, great. And if the compiler is not sure to vectorize, you can help the compiler. And now OpenMP comes into the game. There are pragmas from OpenMP, and pragma OMP SIMD will tell the compiler the next line is available for SIMD operation. And pragma OMP parallel for parallel for SIMD and so on. You can add SIMD at some point if you like, if it's appropriate way. You will see the example with OMP SIMD. You can tell as an example the compiler this for loop is free to be vectorized. And if there are some reduction operations here, if you sum up on the variable sum, you can sum here, and then you need to tell him, okay, it's some reduction operation. But anyway, the comment is SIMD, tell the compiler with OpenMP, do SIMD, and the compiler will do it. And of course, if you do it for a loop which is not contiguous in memory, your code is wrong, and the results can be wrong. So you need to check the results if you do that. Okay, so now we go to an example, and this is an example I will just show you here online, and this is the only example where you don't have to do anything. Okay, I will do at first autos, also SSH autos. It's like in your case, you can go to the system. I go to my program. I open my editor, and let's see. We will go step by step through it, and I open a second window, and okay. So on the bottom window, I hope you can see it. On the bottom window, I execute my script, which I see here above. Okay, what happens in the first? The first is he's telling, oh, I don't want to work. Well, why? Because I'm here on an interactive login node, and on the interactive login node, you shouldn't do code execution. So that's why the first step is I ask for a compute node. I want to change to a compute node. This is what I've done now. He reports about it, but I have now a reservation, and I can see that if I ask SQ, yes, here there's one node running for you. It's telling me status running, and one node is available. I have one node in the reservation for me. Okay, great. And now I start my script, and he tells me, oh, I have prepared ask for the hardware. Okay, then we ask for, also if I ask for cat CPU info, then this is the hardware of the login node, but I'm not interested in the login node. I'm interested in the compute node. And that's why I have to start srun, and I ask for the CPU info on the compute node. This is how I do it. And then, and this is a long list of, also we can see how long it is, because Autos has so many cores. It's really core by core. It's really long. Yeah, you see here it's processor 8, and now for each of the processor, it's a long list. We go, and of course we have more than almost 200. It's a really long list. That's why I asked for the last for the properties only, and this only for the last processor, the last core. I asked for one core for the information. So this is a list of flags which is available on the cores. And now if we go through, where's MMX? So MMX is here. Here's MMX. And SSE, here is AVX is available. And of course, AVX 512, and here's AVX 512. And perhaps here, SSH4A is there, SSH41. So there's a lot of features. So this compiler is available. This hardware, this core is available for vector processing. Great. So I now go to the next example. I evaluate my script again. And I do something more. And now I ask, I have prepared two C files, not aligned. This is my first C file. And what happens here, what you see is, okay, here's a main program. I do some malloc, and malloc for the matrix here is in this line. And you see it's enough memory for a matrix. Now let's ask for the ordering. And I have entered some numbers here. That's the initialization for A, to outer loop and an inner loop for A. And here's the evaluation line. And for this inner line, it's the outer line, it's the inner line, here's some sum. And you see that J is the index which is running, and J is not contiguous in memory. So, and that's why not aligned will tell you, and this is line 33. Remember line 33. What is the report of not aligned? Not aligned tells me, okay, I don't tell you about line 33 because 33 is not vectorized. I can tell you about line 20. Okay, let's look for line 20. Ah, okay. He sees that he connects both lines. It's unrolling in the backyard, and that's why he's able to vectorize with respect to I. And this is correct. He has seen, the compiler is very clever. He has seen is that I is contiguous in memory, not J. Great. Here was a good job. Okay. And the better example is SIMD, is the same code, but with correct ordering. And here the difference is just that the A is transposed. The ordering, I have just stored the data in a transposed way. And now the inner loop is contiguous in memory. J is the fastest index. And that's why line 33 should be vectorized. And what does the compiler tell? Yes. Line 33 is vectorized. Great. Good job. And what did I do then? This is the compilation which we have looked at here now. And now the last example is I take the SIMD code, but I force him not to vectorize. So please do not vectorize. Great. But at the same time, yeah, okay, please do not vectorize. And this answer is, yes, I don't do loop vectorization, but in line 23, I do loop vectorization. As you are forbidden to do it, but I do it anyway. Why? Because I tell him with the help of OpenMP, please, I force you to vectorize this loop. So he is guided by the pragma. So if I remove the pragma and I ask him again, then the answer is yes, I don't do any vectorization. Great. This is exactly. So I correct that. Please do the vectorization again. And here the report is good. Okay. So, and this is all I wanted to show you here. And of course, I have to check the results. Is my result of my code correct? And this is essentially here the check. All of the vectorization should be in a way that the result is the same. I need to check for that. Things can go wrong. And but the major message is for vectorization, let the compiler do the job. Okay. Let's go on. So I go out, I leave Photos, and go back to the slides. Okay, let's go to multithreading. For that, we remember we had seen the architecture model, and the architecture is some cores on our shared memory, and we have one memory block with the different cores. And our programming model is now consisting on threads, and the threads have the shared memory, but additionally they have their private memory blocks. So the program model is offering more properties than the hardware itself. So and here in this case for OpenMP, the parallel units are called threads. Okay, that's why if I talk about OpenMP, I always talk about threads. So and we see private and shared memory. Let's see what the execution model for OpenMP. And an OpenMP model, an OpenMP code starts at some point. Here on the x-axis is time. We start with one thread, so one process with one thread is starting. And at some point, we call it master thread. And at some point, I can fork, I can create other threads. They help the team leader to execute the job. And then I close the team and I can have a scalar evaluation of one thread again. Okay, here's a question about run autos. I will give you, I will show, when we start with the first exercise, I will show you where to download the autos. I haven't given it so far to you. When I start with the first exercise, I will tell you where to download. So, and so they have a parallel region, we have a sequential region where only one thread is available, and we can switch from between both stages in time. Okay, this is what happens in a parallel program. So what do we have to do for OpenMP? If we start with the sequential code, and the sequential code is called seq.c, we compile it with GCC, and OpenMP needs to include some header file. So because we want to start, we want to apply functions from OpenMP, we need to have the headers, and the compiler needs to know, yes, I need to be aware of OpenMP. So please add this command line option, and then you can compile OpenMP code. Okay. Good. So also, please add a header file and change the compilation line. Okay, and for convenience, you can use some environment variable. So if you preprocessor variable in your code, let's call it SEQ and OpenMP, you can write a line which is available for OpenMP and which is for the sequential part, and write it down like that. And if you compile it without OpenMP, then the result is, oh yeah, it's sequential code. Here, that's a print. And if you use the command line option OpenMP, then he takes the code with OpenMP. So you can include both into one code, also sequential and parallel code. So the usual pragma statements are double cross pragma OMP. The function call has the name OpenMP underscore something, and the environment variables as well. So how does the very simplest hello world program look like? Okay, you have some includes, and the include lines, one of the include lines is for OpenMP header file. Then you have your main program. In the main program, at some point, you have a pragma statement, and here the pragma statement is open a parallel region. So before this pragma, only the master thread is available. After, and in the block after OpenMP parallel, you see that all of the workers are working. So this is executed by all of the threads. And finally, main is gone. So what happens if you execute this code? Of course, you need to compile it, but let's assume we have compiled the code. We set the environment variable. We want to choose 2 threads. Please take 2 threads for the next program. We execute the program, and the result is, okay, the print statement will be available. My ID is 1 and 0 and 1. Yeah, why 2 numbers? Because each of the threads executes its own printf statement. So that's why we see 2 lines of output. Okay, And pragmas can be more than, also we have a lot of pragmas. Pragma OpenP parallel is just the simplest one. But usually the standard pragma interface is pragma OpenP and then some name and some additional options, which are called clauses. You can use it in continuous lines behind it to save space. And examples for pragmas like something is pragma OMP barrier, and this pragma is just standing for its for this line alone. Other pragma statements like pragma OMP4 is acting on one line after pragma. So this pragma is used for one line. And then other pragma statements, like we have seen OMP parallel before, this is available for a complete block. So here the block starts with the brackets, and here can be a very long and complicated code block, whereas pragma OMP4 is just for one line. So, and of course, you need to be careful. You shouldn't jump through your code. Go to and some commands are old-fashioned. Please don't do that. The only exception to jump is with the exit function. Okay. And example for a runtime function is something like OMP get num threads. This is the function which tells you how many threads do I have available. And of course, if I have asked an environment variable for 2 threads, the result will be, yes, you have 2 threads. Great. They don't need to be the same, because if the Linux system tells you I have some restrictions, I don't want to give you so many. So then that might be a difference, because then it might be that you have asked for thousands of threads, but the answer is I give you just 192. That might be, it depends on the setup of Linux. And OMP get thread num is here the tiny difference is num threads and thread num. This is the present ID of the thread. So each of the threads has its own personal ID, and so the number, this number is between 0, ranges between 0 and below a number of threads. Okay, and if you want to learn more about or the details about the specific pragmas and functions, you ask the specification. I have told you already, but of course Google and your chat of your choice can help you. Okay. So now we start with the first example, and this is here. So this slide will guide you through the first example. So I will tell you here a little example in detail. You find the example on Otus, and on Otus on the directory /scratch/, and then hello OpenMP. This is the example code. Please make a copy for that. So copy -r means complete the complete directory, and you can copy it to your home. You can copy all of the content of my directory, but just as an example. And if you have copied hello OpenMP to your home, then you can go to this directory, and then you go step by step through the work tasks I've given you. I have prepared for you sec.c, and you will create omp.c, and then can you execute the bash script, and this bash script will submit otus.slurm, and then depending whether you are successful with your code, then you will see the output of the number of threads and hello world and the thread ID and so on and so on. And the output you will see in the Slurm output file. So, okay. And to do that, I give you 10 minutes something. I will go on with my slide in half past 11. So in something like 7 minutes. And in between, you can ask questions. I will be in the chat. Okay, hello. Now things become a little bit more involved. We have seen that we have we can switch between the parallel and the sequential regions, and now we want to deal with private and with shared data. So the default way of variables is that they are shared. So if before I start a parallel region, I can have some variables, something like a b variable here. And if I can tell, okay, please consider b to be shared, and then the variable, the number 1, 2, 3 is available in the parallel block. And of course, because the default is shared, I can even remove this shared statement. This will do the same job. So, and because b is shared, if b is accessed by a read statement only. If I write something to this variable b, then b is shared again. And of course, if two threads write to one variable, it's undefined which thread is the winner. So we call it race condition, or we can call it wrong code. If we write some data to a shared variable, this is the wrong way. And if you start your code twice, the result might be different. Okay, so private and shared is one possibility to control. You can control it. You can tell each variable to be private or shared. And private, if you just tell private, then the value of A is undefined. If you tell first private, B is considered to be first private, then it's B is private, it's not shared anymore, but it is the initial value is well defined. So first private is private and a good initialization. What happens in the back is that this variable is copied to a local version. So, and that's why, of course, you can read and write to B because it's private. So, and last private is a statement you can see in loops. We will see it later. So, default is I have said default is shared, but you can switch on the default to private. So all variables which are not mentioned are then private, and so you can control, of course, B it needs to be shared, forced to be shared, but A can be a private here in this case. And you can, if you look for errors in your code, you can set the default to none. This means the compiler tells you an error. You are forced to define private and shared for each and single variable. So that's why it's a help for you to control private and shared in a very good way. And yeah, now we have discussed now the scalar variables. What happens with vectors, with arrays? And in C we know two kinds, or in Fortran as well. In C we consider two kinds of arrays. And at first we look into a stack array, and stack array looks like that: a double A, and then a bracket defines the size of the array. So, and in this case, it's a very short vector, of course. But if you now make the statement it's shared, then this shared statement refers to the content. So these numbers are the shared numbers. You can access A, and you have the correct numbers in there. If you say it's private, then the complete vector is private. So B is copied several times that you can access the content. So this is specific to stack arrays. So if our arrays are located on the stack, if you do the same on heap arrays, things are different, because heap arrays are created with a malloc statement. You have no control with shared and private to the content. So if you now write shared A and private A, the vector is meant. So the vector A for the pointer of the vector is meant. So not the content is shared and not the content is private, but the pointer pointing to the memory is mentioned. So if you want to now use located or private arrays, you need to invoke malloc within the block, within the parallel block. Now each thread needs to make the malloc statement for itself, and of course the free statement needs to be invoked in the same block. So So it's an important difference between stack arrays and heap arrays. And then the really important thing is if you work with static variables are by default shared because static variables are located on the stack, and this is a technical background for that. But static is kind of you don't expect that static variables are shared, so you really need to know that. This might be a cause of errors in your code. So that's why I go more into the details of static variables. We consider the static and the dynamic extent of our code, which means the static extent is the code lines which are written in our main program, but the dynamic extent is the code which is hidden in function calls. So the dynamic extent of this code example is the content of my function. So, and even if you have variable declarations in the dynamic extent, this static statement forces the variable to be shared. And this is really what you don't expect, because once you are writing this function and you use static, you never think of, oh yes, I will parallelize my code in 2 years. So using static is, for parallelization, it's difficult. Okay, where can this happen? And the example for that standard example is something like random generation. A random generator has its own status. A random generator remembers, okay, I'm in my random status, and that's why a random generator likes most often have some static variables within it, and that's why random generators behave different so this kind of random generator behaves different if you use it in parallel, in OpenMP parallel or not. And how can you see that? In a parallel environment, you open a parallel for OpenMP parallel for, and you invoke the function myRandom and myRandom due to this coupling of the static variables. The code is different working for OpenMP and for the sequential way. So how can you solve this? You can solve this that you invoke your function only in the sequential part, so it's before the start of a pragma. You apply the function myRandom. You can store it in some data place, and then to use the data, the pre-evaluated random numbers you can use in your parallel environment. So and how can you imagine is data transfer working? You have now different threads, and you can copy data from one to the other thread if you read and write to shared data, and you do it in a way that you can control the timing, that the first thread is the thread who is reading needs to know that the other thread has written already before. How do you do that? You do that with synchronization. So you have synchronization properties like barrier, critical, or atomic. And how does that work? You go okay, now it's a wrong example. If you go into some parallel region and you want to write something to depot. Also here you read from depot, but if you want to write there something, you need to make it very clever, and the thread ID 0 writes something to depot. At first depot is a shared variable. Then the first thread, also 0 thread, is writing something. Then we have a barrier, and after this we know that thread 1 can read depot, and the result is the correct which is here. So you need to synchronize both threads, that the timing between writing and reading to depot is controlled. And you have different more properties to control timing, or that access to data is atomic, for instance. the following line is atomic is only acting to one line, and you know that this line is executed by one thread at each time. So this is kind of not being in parallel. And critical is the same as atomic, but you can apply a complete block. So the block is controlled to be evaluated by one thread only. And what is here? Hier ist also Single one single. Also hier pragma single is that only one thread is evaluating this line, and automatically all other threads waiting after this at a barrier. Then here in this line, all of the threads doing this job, but one after the other. Here is a barrier. And at that here again, one single thread is executing this. And single does not mean it's a master, it's just one thread which is available. Okay, so this is data control. And now we come to the business why OpenMP was created a long time ago. It was for parallelization of loops. And what we can think of is, let's assume a loop, a for loop, which is makes just some silly copy between B and A. And of course, if we go now into a parallel region, we know that the complete parallel region is executed by all of the threads. So in this example, 2 threads, both threads do the complete job. So essentially nothing is better because it takes the same time to evaluate this. And but how will you do? How can you do it to distribute the work? You need to add a new pragma, a second pragma, not only OMP parallel but parallel OMP 4. So this pragma tells the compiler, oh, please distribute the work to the 2 threads. So now thread 0 is evaluating half of the loop, and thread 1 is doing the other job. So, and this is really then has the property that it can run faster. And to do it, to write it shorter, of course, this is the correct way, OMP parallel, OMP 4, and you can merge both lines into one. So OMP parallel 4 is the same. And now you can control loop execution with additional options like jump size, static, and dynamic. And most important here, static and dynamic is you can ask where's an example? Okay, no. You can ask static and dynamic that are different. A static tells the workload distribution is decided during compile time. So once your code is running, there's not so much overhead, no overhead deciding about the ordering of the threads. Dynamic is more involved. There's some administration in the back. And here the decision of loop execution is done during runtime. And if you need that, you need to do it. But usually you want to do it static, because your code should be as fast as possible, and that's why static is the choice which you should prefer. So you can control this on the pragma here, giving the OMP4 schedule static or dynamic, and you can control it as well on the command line before you start your code. My recommendation is I use for parallelization always schedule static, and so this is usually the line I write in my codes: pragma OMP4 schedule static. Because the default is not defined in the standard. The default for schedule is compiler dependent. Okay, and the C language is very, very rich. You can do a lot of things with a for loop. That's why within the for loop, lots of things can be hidden. And that's why OpenMP says, well, don't do so complicated loops. For OpenMP, just keep it simple. Yeah. And for keep it simple, it tells me, okay, this a for loop should look like a very simple for loop. So you have some initialization, like it starts at some 0 point. You have some increment operator, which is something like plus plus or something plus plus equal. So very simple incrementation. And the breaking the break option should be a very simple function. Okay, good. This is the idea. And of course, each of our example for loops are as simple as we can think of. So, and what can happen in such a loop? What can go wrong? Okay, here in this example, nothing can go wrong. Also, be aware that after closing the for, automatically we have a barrier. This is included anyways, so because to avoid errors in your code, to switch off this barrier, this automatic barrier, you can add no wait, but be aware some of the threads might go on and do the work while other threads still are in the for loop. You should not use a too early then. Okay. So and last private, now here we see last private. If last private for applies to a variable, then the value of this variable is this one which you expect for the sequential execution. So yeah, what you should expect. Okay, great. What can go wrong? Things can go wrong in for loops. Something like I have here defined in some reordering index j, and I use the reordering j to reorder the indices for the vector b, and this is no problem because you access b of 1 2 times, but it's only a read action. That's no problem. Problems appear if you write, because here j of 1 and j of 2 is 2 times the same value. So a1 writes to the same space in memory. That's why here's a race condition. You write to the same space. We know that. This is dangerous. Okay. And also this is wrong. This is wrong code. And to do it right, this reordering of indices needs to be a complete permutation. And if it's a permutation, you have no race condition, and of course you can write it. So be aware of that. And of course, if you have something like recursive dependencies, things can go wrong as well. So AI and AI plus 1, they might depend on each other, because if you are start the loop with I0, then I0 depends on I1. So and only after that A1 is changed. So this the value of the vector depends on the ordering of evaluation of loop evaluation, and that's why you need to solve problems here. And one solution to do it in parallel is to introduce an intermediate vector, an intermediate array. And in the first, you copy everything to the B vector, and in the second, you do this operation. And now, yeah, then you can resolve this dependence. But there are examples. Okay, but then there are examples which are too hard, because here it's recursive. Here, in this case, you cannot solve it even with an intermediate array. So it's essentially an algorithm which doesn't like to be parallelized. Okay, and let's see what happens here. Here's also a simple Jacobi iteration. You see that index movement is possible because you don't write to the index, but yeah, and Gauss-Seidel iteration, then the evaluation is dependent on the ordering of the loop, and that's why you need to add some more pragma. And finally, it's sequential code in your case. Okay. So now the last important statement is be aware of aliasing, because you can write in this example, you can write in your code a nice loop which looks not so difficult because it's a for loop with 3 arrays, very easy. And these arrays appear in a subfunction A, B, and C. But in C, it's possible to overlap these memory areas. So A, B, and C are not independent. And if you look into this call, this whole issue is located almost on the same space in memory because A is x of 1, starts at this point, B starts at that point, and C starts at that point. So finally, if you write it down on paper, you see that in the end it's Gauss, it's a Gauss iteration. So it is not possible to parallelize. You know that already. So this seems to be a good code to parallelize, but in fact you cannot. And that's why you need to be really aware of aliasing that arrays do not overlap. In Fortran, this is not allowed. In C, this overlapping of memory arrays is part of the game, and that's why in C you can forbid aliasing and once you add the restrict. And this tells essentially the code developer, oh, here in this case I can trust A, B, and C do not overlap. Okay, and I will not go into the details here, but yeah, no, I will skip that. Functional parallelism, and I want to go to our example, to our last example or the next example. We have timing in OpenMP. We can measure the time once we have code which we want to measure before our code block and after our code block. We ask the OpenMP function about the timing, and then the difference is the time in seconds. So, and this then is the offer for me for the next example, and I can solve this example and showing you the result because we will solve the problem later.